we're going to talk about using NMR spectra to determine the structure of a molecule. And we can use nuclear magnetic resonance from several different atoms, many different atoms, but the most common are hydrogen and carbon-13. Hydrogen NMR is also called proton NMR. And one of the powerful things it does is let us tell the difference between this isomer and this isomer. Both are C3H7Br, but they will have two different spectra. I can assign these hydrogens, 1, 2, 3, 4, 5, 6, to this peak right here, and this hydrogen to this peak, because it has to have a hydrogen. Or I can assign these two hydrogens to this peak, and these two hydrogens to this peak, and these three hydrogens to this peak. So I'm able to figure out, by looking at the structure, which of the two isomers I have. And that's the power of NMR. And it can handle very complex molecules, but we're going to limit ourselves to simple ones. So first, a little background. If the nucleus of a hydrogen atom, or a proton, which is the nucleus of a hydrogen atom, is hit with the right radio frequency, it causes this to flip. So what happens is that it's in a magnetic field, and the radio waves are absorbed, causing this flip into the higher energy state. And then as it relaxes back to the other original state, the same amount of energy is given off. And that given off is what's detected by the detector. The same way we can measure light given off in a gas discharge tube. The thing that makes it unique is that every hydrogen's surroundings impact what frequency causes that jump. So a chemist can look at this picture and see that at just above 7, there's a peak that corresponds to the hydrogens that are on the benzene ring. And that just above 2, there's the 3 hydrogens that correspond to the methyl group. And you'll always see something right at the 0, because that's what we put in as our standard. So here's what an NMR machine looks like from the inside. There is a quickly spinning sample tube. These tubes are ridiculously expensive. And it is between the poles of the magnet, and there's some radio frequency hitting it. And that whole system has to be kept very cold for the very powerful magnets that we're using. So we have the magnet, and it's inside liquid helium at 4 Kelvin. And to keep the liquid helium cool, we have liquid nitrogen. And to keep the liquid nitrogen cool, we have a vacuum chamber. So we have a system set up that is quite large to keep this superconducting magnet very, very cold. For one that has a lower magnetic field, we don't need quite the refrigeration system. When we look at NMR, the pure liquids are too concentrated typically, so we're going to make a solution. And most of our solutions, if it's polar, we'll use something like water. That's our most common solvent. If it's nonpolar, our most common solvent would be chloroform, like this. It's slightly polar. But instead, we can't use hydrogen because hydrogen is what the NMR detects. We don't want the hydrogen from the solvent to interfere with the hydrogen from the solute. So our solvent would be D2O, deuterium, instead of hydrogen or heavy water. And for our nonpolar or less polar solvent, we would use deuterated chloroform, CdCl3. So we can use a chart to figure out where the shift is. It's not like we're going to have to memorize what those kinds of numbers are. And so here's a piece of the chart. Also, we have to figure out which hydrogens are identical. So to figure out which hydrogens are identical, I'm going to take a look at this model right here, first molecule, and I'm going to say that these 6 hydrogens are identical because they're all CH3s, both coming off the same carbon. The next one is this one. It has no other hydrogens like it. And then the last pair are these. There are 2 hydrogens, and if you looked at this in 3 dimensions, you would not be able to tell the difference between one hydrogen or the other. So I'm going to give them letters, A, B, and C, and I have 1, 2, and 6. So there's 6 A hydrogens. Last one. There is 1 B hydrogen, and there are 2 C hydrogens. That's one of the harder things we have to do. The next thing we do is we figure out what it looks like and figure out on the chart where its parts per million are. So I'm going to start with my C hydrogens. My C hydrogens are next to a bromine. So that is what I have right here. It's a hydrogen next to a halogen. The carbon is attached to a halogen. So I'm going to say, whoop, undo, gave it away. It's between 2 and 4. Then I'm going to say, I'll take a look at my B, what I labeled B, and it's a carbon, it's a hydrogen attached to a carbon that's attached to 3 other carbons. That's this one. A hydrogen attached to a carbon attached to 3 other carbons. That's between 1.5 and 2. And then the ones I colored in yellow are part of a CH3. And that'll be at about 0.9. And that's how this works. We figure out what the equivalent hydrogens and then figure out where they'll be. So let's do the same thing for another one. I'm going to say that these 3 hydrogens are identical. Oops. I'm going to say that these 2 hydrogens are identical. They're on a carbon between a CH3 and a CH2. I'm going to say that these 2 are identical. They're between a carbon with a CH2 and a carbon that's part of a carboxylic acid. And that last one is unique. So I have 4 letters with equivalent hydrogens. And now I look at my chart and figure out where they are. My 3 that are part of a CH3. That's this one. My 2 that are part of a CH2. My 2 that are part of a CH2 also might be here, but I'll tell you a little more about it in a minute. And then my alcohol, that's so dark, but is right there. That second one I gave a 1.3 plus, meaning it's going to be a little more parts per million than 1.3 because being close to this group makes it a little higher in parts per million. Essentially, the closer it is to an electronegative element, the higher in the parts per million. Let's take a look at this benzene ring. I gave it 4. A. Oops. B. C. And D. And remember, I'm not looking at those carbons that are the intersections. I'm looking at the hydrogens that are coming off of them. And so I have 1, 2, 2, 1. And if I find the oxygen on the OH, that's this one. Air stands for aromatic, so that's between 4 and 7. B, C, and D are aromatic or a benzene ring, or they're calling it a phenyl ring. It's a synonym, between 6 and 8.5. And again, the one that's closest to the OH, I gave it an 8.5 plus. Benzene rings are tricky because sometimes their peaks will overlap and you can't even tell them apart, and sometimes they'll be separated. So I'm going to pause and have you try the next two. All right, is this what you got? You should end up with a 1 to 2 to 3 ratio. And it doesn't matter if you label the ABC to left to right or right to left. And then on the right, with propane, you can see that the CH3 on either end is identical. You're only going to see 2 peaks. And we're going to talk about this in a few minutes, they're in a 3 to 1 ratio. So when we look at the ratio, you're not going to see 6 to 2. You'll see 3 to 1. All right, the next thing is that, and there's a pretty complicated picture up there showing that depending on what it's next to, the peak can be split because sometimes the magnetic fields align and sometimes they're opposite each other for neighboring hydrogens. So this is my B hydrogen. These are my C hydrogens. These are my D hydrogens. And these are my A hydrogens. So let's take a look at splitting. First, my B hydrogen is split, if we enlarge this, into 1, 2, 3, 4, 5, 6 little peaklets. And if we look at my B hydrogen, which I'm going to color yellow, it has 1, 2, 3, 4, 5 near neighbors. Let's take a look at my C hydrogen. I'm going to erase these colors. And I'm going to color that one blue. And it has split into 5. Split, 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 split into 5. And if I count its near neighbors, it has 3 here and 1 here. 4 near neighbors. And by near neighbors, I mean hydrogen atoms that are on a carbon next to the carbon that has the hydrogen we're talking about. So here are our hydrogens we're concerned with. Find its carbon, go to the carbon next to it, and look at its hydrogens. So that gives us more structural information. I know that my B is surrounded by 5 near neighbors. I know my C hydrogen has 2 near neighbors. Actually, I have A and D backwards. A and D. A, my CH3s, have 1 near neighbor because it's split into 2 peaks, and D has 2 near neighbors because it's split into 3 peaks. Those little numbers above it, that's telling me how many identical hydrogens there are. So there's 1 B hydrogen, 2 C hydrogens, 3 A hydrogens, and 3 D hydrogens. Let's take a look at it again. If I have a CH3 next to a carbon attached to 3 different things, it's split into 1 peak. If I have a CH3 down here that's next to a carbon that has a hydrogen, it's split into 2 peaks. If I have a CH3 that's next to a carbon with 2 hydrogens, it's split into 3 peaks. If I have a CH2 between two CH3s, or CH2 and a CH3, then it could be split into even more peaks. And the intensity, you saw that if there's 2 peaks, they're equal height. If there's 3 peaks, it's in a 1 to 2 to 1 ratio. They follow Pascal's triangle. So you have a single peak, or 2 peaks of equal height, or a 1-to-1 ratio, or a 1-3-3-1 ratio, or a 1-4-6-4-1 ratio. And we're going to be approximate when we're sketching these. We're not going to draw them exactly. So let's take a look at the splitting for the ones we've been talking about. Our A hydrogen use the pen. Our A hydrogen is next to a carbon which is attached to a carbon with 1 hydrogen. So it's going to be split into 2. Our B hydrogen is attached to a carbon, which is attached to a carbon with 3, a carbon with 3, and a carbon with 2. So 3 plus 2 plus 3 is 8 plus 1. It's going to be split into 9. Wow, it's going to be just sort of look like a mess like that. And our last hydrogen is attached to a carbon. Let me use a different color. The hydrogen is attached to a carbon with 1 hydrogen. It's going to be split into 2. That gives us more information about the environment. We can do the same thing with these two. This set. Our A hydrogen is attached to a carbon, which is attached to a carbon that has 2. So it's going to be split into 3. Our second hydrogen is attached to a carbon that's a CH3, and attached to a carbon that's a CH2. 3 and 2 is 5. It's going to be split into 6. And let me erase because it's too messy to look at. Our third hydrogen is attached to a carbon, which is attached to a carbon that has 2. It'll be split into 3. And our fourth hydrogen is attached to an oxygen. There's no splitting at all. So you try the next set, and we'll take a look at them. Okay, let's take a look at what we've got. This one is surrounded by a CH3 and a CH3, so it will be split into 7. And this one is split, it's got 2 near neighbors, so it's split into 3. All right, last little bit. There are numbers above, and those numbers above, or you might see it, so it might be above like this, or it might be like this, or it might have a drawing like this where you're actually measuring the heights of the ratios. This tells us the ratios of the areas under the curve. The computer calculates that and gives us a ratio. So we know that the first one is in a 2 to 3 to 3 ratio. It doesn't mean that there's 8 hydrogens. It means that there's 8 or 16 or 24 or some multiple of 8. So that's the basics you need in order to read NMR. If you need help with it as you read the next NMRs in the next video, then let me know. Good luck.